Okay, cool. So general solution to a trig equation. We've pretty much done this anyway. We talked about it last lesson a bit, but I'm going to remind you and I'm going to formalise it so that you can answer questions on this, and then you'll be done on all the review trig stuff basically, and then I'm going to introduce you to some new friends. So, a trig equation, as we know, has an infinite number of solutions. Obviously I can't draw an infinite number of solutions, but hopefully you can see with my negative cosine curve there that if those arrows do go on forever, where each of those yellow highlighted bits represents a solution to negative cos x equals a, where a is just some point on the y-axis, then you'll have an infinite number of those yellow dots, because it's just going to keep on repeating over and over and over again. So that causes a problem. If you're just asked to find all the solutions, that's a problem. But we can represent all the solutions generally if we need to create a generalisation, which might be handy in something like where you're using a trig function to periodically predict high tides or low tides or tidal points or moon phases or positions on a Ferris wheel or any of those contexts where you don't just want to know for the next hour, but you want to know generally so you can pinpoint it at any time in a year or 2 years or 10 years. So here's my first question. What are the 10 solutions to the equation sine x? What are 10 solutions to the equation sine x equals a half? How could we write this generally? This is where we're going to build up our understanding. So that's zooming funnel. There we go. So I'm going to do some of this with you now, and we'll talk about these solutions. So sine x, first of all, equals a half. And to solve this, you might remember, hopefully you remember this from math methods, and we talked about it a bit last lesson. We do sine inverse of a half, and sine inverse of a half is pi on 6. I'm going to do this in radians. We need to start getting better at using radians and more consistently. Pi on 6 is about 30 degrees, so it's equal to 30 degrees. Well, it is 30 degrees. It's equal to 30 degrees, but we're going to use radians. Now, if I go to my unit circle and draw my cast diagram, CAST, my first solution is pi on 6, and sine was equal to a positive value. So we're looking for the quadrants where sine is positive. It's positive in the first quadrant and it's positive in the second quadrant. That's what the cast rule tells us. So the other solution is here. And that angle is, this is pi on 6, which means that this is 5 pi on 6. So we have two solutions. One is pi on 6, the other is 5 pi on 6. And we get our full range of solutions. So if we're going to get 10 more, it's really easy. We just need to add or subtract 2 pi to each solution. And this is my first stream of solutions that comes from the original. I really wanted that to be red, but it's not going across. There we go. And this is my second stream of solutions. That comes from the cast diagram. I've got first quadrant, second quadrant solutions here. And now I'm going to add 2 pi. And keeping in mind, of course, that 2 pi is equal to 12 pi on 6. That helps me with my addition because now the denominators are the same. I get 13 pi on 6, and here 5 plus 12 is 17 pi on 6. Now if I add another 2 pi, which is 12 pi on 6, I get 25 pi on 6, or I get 29 pi on 6. If I add another 2 pi, I get 37 pi on 6, 49 pi on 6. Here I get 41 pi on 6. Here I get 53 pi on 6. The question did ask me for 10 solutions. I've now got 10 solutions. But the question goes on further to ask me, how could we write this generally? So that's my question to you. The system is we find our first solution using our calculators or using exact values. We find our second solution using the unit circle, and then we find any other subsequent solutions by adding or subtracting 2 pi. How do we write that generally? I'll start with this. Plus or minus 2 pi, what, sorry? N? Plus or minus 2 pi n, where n is, and you can even say n is a natural number. I'll use integers, but keep in mind either we can say pi on 6 plus 2 pi n, where n is an integer, which means it can be negative, or you could just write pi on 6 plus or minus 2 pi n, where n is a natural number. So you can do either, and I've done a mixture, which is also fine, it doesn't really matter.
Wait, is natural numbers only positive numbers? Positive integers?
I could do the positive integers, and that would be then be n.
Natural numbers is positive integer, then 0.
Okay.
Yeah, so I could do that, either one. Just make sure that you're not cutting off the solution. So if I said pi on 6 plus 2 pi n, and then said n was only a positive integer, I'm cutting off half of the solutions. All the negative solutions I've just cut off. So whatever representation you use, just make sure you're not cutting off those solutions.
What is 0 an integer?
0 is an integer, yes, but it's not a natural number, and it's not in the positive integers.
Wait, it's not a natural number?
No, the counting numbers start at 1.
Not 0 and
Wait, so 0 and negative?
So in fact, you're probably better off having that and having that. We're probably better off having that. 0 is not negative or positive. And you can fight about that all day long. It doesn't really matter. It doesn't worry me. It's the same as whether 1 is prime or not prime. It's definitely not prime, but some people will fight with you about it.
I swear you put on the one note that 0 was natural number.
Yeah.
0 is a negative number.
Natural.
Oh, natural. Oh, maybe I do. Yeah, but it's not in the positive integers because 0 is not positive.
Yeah.
Okay, so here's the process, and here are my solutions that I've written out previously. So the process is solve the equation for the first solution, find the second solution using the unit circle. The generalised solution will be plus or minus 2 pi n, where n is a natural number and 0 is a natural number, it's not a countable number. Sorry about that. Or plus 2 pi n, where n is an integer. That's your process. A note here. The textbook uses a somewhat simpler way. I can't remember the way that the textbook uses. You need to recall a different process for each. Oh, I see, yeah. So the textbook uses a memorised way of doing it. Instead of using the unit circle, they just say if it's sine, then you get this or this. If it's cos, you get this or this. If it's tan, you get this or this. So you can either memorise 3 ways using sine, cos or tan individually, like the textbook does, or you can know one way and be aware of how to use a unit circle. That would be, in my opinion, a better way, but that's up to you. Hence the you decide smiley face there. And here's example 3. Harvey, time?
8 minutes.
Left? 7 minutes left. Okay, determine the general solution in each case. A, 2 cos x equals negative 1 gives me cos x equals negative a half, and that gives me x is equal to cos inverse of negative a half, which of course everyone will know that's not in the first quadrant because it's a negative. So if I do that in my calculator, it will actually give me a second quadrant answer, and because it's cos, it will give me 2 pi and 3, I believe. So it should give me 2 pi and 3. If I go to my unit circle and do my cast diagram, in this case I'm working in it's given me the second quadrant. The other place where cos is negative is in the third quadrant. If I mark that in here, I get 2 pi and 3, which is that angle. And the other angle is there. This is pi on 3, which means that this is pi on 3. That's pi, and this is 4 pi on 3. So I get 2 pi on 3 or 4 pi on 3. And this is for the generalised solution. All I need to do is find my first two solutions, and then therefore x is equal to 2 pi on 3 plus 2 pi n, or 4 pi on 3 plus 2 pi n, where n is an integer. Job done. So that's my generalised solution. I just had to find the first and the second. In this unit circle here, I know some of you have done this and have started doing this anyway. Cos has got a really nice symmetrical relationship because it's an even function. And so because you get 2 pi and 3 here, then negative 2 pi and 3 is the other solution. So you can also go backwards from 2 pi by 2 pi and 3 to get your 4 pi and 3. Another way of doing it, about equal in terms of time, so that's up to you. Question B, tan squared x minus 3 equals 0. Gives me tan squared x equals 3. Tan x equals plus or minus the square root of 3. Don't forget the minus. As soon as you take a square root, 2 possible solutions. You've got a minus solution there as well. And x is equal to tan inverse of root 3 or tan inverse of negative root 3. I've got to split it there because my calculator can't deal with them both at the same time. Tan inverse of root 3 is pi on 6. Tan inverse of negative root 3 will give me the fourth quadrant answer, which will probably give me negative pi on 6. And if I draw those on a diagram, you'll note here that I actually get all 4 quadrants because I've got my positive answer and I've got my negative answer. So it's going to give me the 2 positive quadrants and the 2 negative quadrants here. Oh, that shouldn't be pi on 6, so that should be pi on 3. So I get pi on 3 here, and I get negative pi on 3 here. They're 2 of my answers. This answer here tracks to the second quadrant, because according to the cast diagram, tan is negative in the fourth and the second, and that gives me 2 pi on 3. And this answer here tracks to the third quadrant, and this is pi on 3 as well, so that gives me 4 pi on 3. I'm rushing this a little bit because I'm assuming you know how to do these equation solving stuff, but ask me if you need to. And so my answers are x is equal to pi on 3 or 2 pi on 3 or 4 pi on 3 or 5 pi on 3, because this is negative pi on 3, or it's 5 pi on 3. And in a general form, I get pi on 3 plus 2 pi n, or 2 pi on 3 plus 2 pi n, 4 pi on 3 plus 2 pi n, or 5 pi on 3 plus 2 pi n, where n is an integer. You might think there might be a clever way of writing this in a shorter form because there's 4 possible streams of answers, but because 3 pi on 3 and 6 pi on 3 aren't represented, there's not really an easier way. We can't just simplify this a great deal. So realistically, you've got to leave it there. Last one. Question C. Harvey? How long have I got?
Be quick.
How long have I got?
A minute and 30.
I'm not going to do it. Sine 2 x minus pi on 3 equals root 3 on 2. Okay, here we go. Speed math. 2x minus pi on 3, sine inverse of this. It's an exact value, so hopefully you recognise that. That's equal to pi on 3 again. I feel like I'm repeating myself. The 2 out the front, I don't touch that yet. I deal with the unit circle first, and then I do the rearrangement. But I'm going to have a period change as well.
Hurry up.
Pi on 3 there. All stations to central. So I've done it the wrong way. Cast diagram. All stations to central. Cast diagram there. That's pi on 3. My other positive quadrant is here. That's 2 pi on 3. Check it out however you want. So I get pi on 3 or 2 pi on 3, which means that x minus pi on 3 is equal to pi on 6 or 2 pi on 6, because I've divided 3 by 2. Now I add pi on 3, I get x is equal to pi on 6 plus pi on 3 is pi on 2. 2 pi on 6 is pi on 3. Pi on 3 plus pi on 3 is 2 pi on 3. They're my 2 solutions. If you're interested in noting here, that is
You've done it.
60, 120, 30, 90, 150 in terms of degrees. I'm just going to finish it. And that's my x. My generalised solution now, my last little step here, is pi on 2 plus pi n, or 2 pi on 3 plus pi n, where n is an integer. I'm finished there. Does anybody have any comments or anything they're upset about in what I've just written?
Yeah, you're going to say with my time. Also, how do I make it tan squared?
Hold on a second. I'll answer that question in a second. Does anybody have any comments about what I've just written? I've done something different.
Did the pi instead of 2 pi because you followed the
Excellent. Can everybody just take note of that? Because I had sine of 2x minus pi on 3, when I divided by 2, that halved the period. So now my generalised solution, instead of adding on 2 pi n, will be adding on pi n. The 2 halved the period. So you've got to deal with the change in period as well. There's an example. If you get one in the textbook, please ask me. Make sure you know how to do it. Sorry I rushed that, but I made a mistake in asking 2 gentlemen to time me, and they put a lot of pressure on me.